Okay, so now we're going to step beyond kinetics and we're going to talk about something called equilibrium. Equilibrium is a huge topic in chemistry. It's probably one of the toughest topics that's taught in first year college chemistry. We're not going to do that much detail with it though. Sometimes reactions go entirely to completion. If you burn gasoline, it's going to burn until the gasoline's gone. That is a complete reaction. All the reactants are used up according to whatever the stoichiometry is. However, some reactions don't do that. They don't use up all the reactants. They set up what's called an equilibrium. When a system is at equilibrium, it is balanced. It's like a seesaw. What happens is the rate, so we talked about rate with kinetics, the rate of the reaction going one way is the same as the rate going in reverse. And so the rate at which they change is the same, which means it kind of gets to this vicious circle kind of thing that a reactant turns into a product turns back into a reactant. They go back and forth, continuing to react, but they don't change the amounts. So the molecules are constantly in motion, trading between reactants and products at the same rate. When a reaction creates an equilibrium, it goes forward at the same rate, the same speed as the goes in reverse. And they'll use a double arrow. You'll see that a lot. And that's the way I'll draw it. I'll draw it like this. It means the reactants turn into the products at the same rate as the products turn back into the reactants. And when an equilibrium is established, it's a very touchy system. It's a very sensitive balance between the reactants and the products. And they respond to changes in their environment in stresses. Those are called stresses, by shifting in the direction of reaction to accommodate the stress. So that's LeChatelier's principle. If a change in conditions, stress, is put on a system at equilibrium, the equilibrium position will shift to reduce the stress and reach equilibrium again. So how can you stress it? Well, you can change the pressure if it's a system of gases, change the concentration of the reactants or the products. You can change the temperature, and you can add a catalyst. That's not on the list, but you can add a catalyst too. All stress factors shift the reaction in order to reestablish the balance. And a shift, this is important. It means that the reaction reacts predominantly in one direction to reestablish the balance. Once it reestablishes a balance, it stays there. It's back at equilibrium again. So if the equilibrium shifts left, the amounts of the reactants are going to increase and the products will decrease until it gets balanced again. If the equilibrium shifts right, the amounts of products are going to increase and the reactants will decrease until it gets balanced again. So changes in pressure only affect systems that have gases in them because gases are susceptible to pressure. An increase in pressure, which is the same thing as decreasing in volume, will cause the reaction to shift to the side of the reaction with less moles of gas. Decreasing pressure does the opposite. It's increasing the volume and it shifts to the side with the most number of moles of gas. For example, if I had that, increasing the pressure by decreasing the volume is going to shift to the side with the least number of moles. I see 1 mole here, 2 moles here. It will shift left, which means the concentration of N2O4 is going to go up and the concentration of NO2 is going to go down because it's going to shift primarily in that direction, meaning it's going to react this way for a while until it gets itself rebalanced. Decreasing pressure by increasing the volume is going to shift to the side with the most number of moles over here. So it's going to predominantly react in that direction. NO2 is going to go up, N2O4 is going to go down, and we say it shifts right. If you change concentration, adding a reactant will shift their equilibrium towards the products, which means shifts right. Adding product will shift the equilibrium back towards the reactants. It will shift left. Removing the reactant will do the same thing. It will shift the equilibrium back towards the reactants to the left. Removing product will shift the equilibrium towards the products, shifting right. Changing temperature is a little bit tricky. It depends on whether the system is exothermic or endothermic. Decreasing temperature removes heat. If it's an endothermic reaction, the shift goes left to make more reactants. If it's an exothermic reaction, the shift goes right to make more products. If it's increasing the temperature, it does the exact opposite. If it's endothermic, it's going to shift to the right to make more products. If it's exothermic, it's going to shift left. So for example, increasing temperature. Here is my heat. It is an endothermic reaction. I want you to think of this as being like on the seesaw. Okay, I'm adding heat. It's upsetting the balance. When it upsets the balance, it has to shift to the right to rebalance itself. Decreasing temperature is going to upset the balance, and it's going to shift left to rebalance itself. Adding a catalyst speeds up any reaction, but it does not shift the equilibrium. KEQ is something we're going to talk about in the next lesson, so I'm not even going to worry about that. It's constant unless the temperature changes. And so I'm just going to kind of skip that. So how would the following equilibrium shift under the following stresses? So here's my equilibrium. I notice, first of all of them are gases, and my heat term is over here. Okay. If I add more chlorine, it's going to upset the balance, make it heavier on this side. It's going to have to shift to the left. If I increase the pressure, pressure only counts for gases, and I count 2 moles of a gas here, 1 mole of a gas there. Increasing pressure shifts to the side with the least number of moles. It's going to shift left. Increasing temperature shifts to the side to compensate for the increased heat. So in this case, it's going to shift to the right. If I took the PCl3 away, and again, it was balanced. If I take the PCl3 away, I'm going to have to shift right to rebalance it. So let's do this one. See if you can stop the movie and do it. All right. First of all, I notice everything's a gas, and my heat term is over here. If I increase N2, it's going to upset my balance. It's going to shift to the right. If I remove H2, it's going to upset the balance, shift left. NH3, shift left. Increase temperature will shift left. Increase the volume, it's the same thing as decreasing the pressure. We'll shift to the side with the most moles. I see 4 and 2. It's going to shift left. Adding a catalyst does nothing. When it shifts, the way it works is if it's on that side of the arrow, if it's on the right side of the arrow, it's going to go up. So NH3 is on the right side, it's going to increase. N2 is on the left side and it's shifting left, so it's going to increase, and NH3 is going to decrease. Increase, increase, decrease, increase, decrease, decrease, and no change.